Hi everybody, welcome to Test 3 review in Calculus 3. As always, you will see the topic of the question on the top. First, we have double integral in rectangular coordinate. So we have some problem like this, the double integral dx dy. So this in rectangular coordinate. First, we will do inside out, and then the first one we have dx inside, meaning that this is the limit for x, and the outside dy will be the limit for y, and we're going to do the inside first. So when we integrate this with respect to x, we will treat y as a variable. We treat y as a constant. Cosine y is a constant. So integral sine x is negative cosine x. And integral of a constant will be that constant multiplied by x. We'll evaluate from x equal to 0 to x equal to 19 pi. And whatever we have, we still have the integral from 0 to 4 pi of dy. So inside out, with respect to x, y is a constant. Right. So we're going to put 19 pi into x, and then 0 into x. And then 19 pi in for each x and 0 to that x. Right. Right. When we put 19 pi in here, cosine of 19 pi, that is like cosine of pi, and cosine of pi is negative 1. So I will just write cosine of 19 pi is negative 1 with an extra negative. It's going to be 1. And put 19 pi here, we have plus cosine of y times x is 19 pi. So that is where we put in 19 pi. Now when we put in 0, cosine of 0 is 1. And we have negative 1. So I will have negative 1. And put 0 in for x, cosine of something times 0, that is 0. So we just have 0. And then dy. Yeah, so we put 19 pi for x, and then put 0 for x. That's why we have subtract them. Next, 1 minus negative 1, so that is the 2. So that gives us 2. And then 19 pi cosine of y. Dy. Now integrate with respect to y. 2 is going to be 2y. And then cosine is sine. Integral of cosine is sine. And we will evaluate from 0 to 2 pi. And of course that will be the values for substituting for y. So put 2 pi in here. I'm sorry, that was from 4 pi. So put 4 pi in there, we have 8 pi. I'll just write 2 times 4 pi plus 19 pi sine of 4 pi. So that's where we put in 4 pi. And then we put in 0. 2 times 0 19 pi sine of 0. Right. Sine of 4 pi is 0, so this one go to 0, this is 0, and this is 0. All we left with a pi. We only left with a pi. So that's what we have. Right. So integrate with respect to x, y is a constant, and integrate with respect to y, x is a constant, and vice versa. Right. The next one is also integrate double integral. Evaluate double integral. So this one is a little bit different than the previous one. This problem we can use forbidden theorem. Right. Forbidden theorem. In order to use forbidden theorem, two things must hold. The constant limit. So must have constant limit. We do have here. And the second part is the function must be separable. Right. So what we mean separable? Separable is when we can write the function here as a product of x and a function of x and a function of y. So we have a function of x and then a function of y. So that is separable. So in this case, we have a constant limit and we have separable function. So we can use forbidden theorem. Let me do this first. Right. Let me just copy the problem first, and then we'll see how the forbidden theorem works. Right. Again, it is inside out. We have separable function and we have constant limit. Right, this is what we do. First, for this dx, we have this integral, and for dy, we have this integral. Right, again, inside out. And the nice thing in this problem, forbidden theorem says we can interchange dx dy without the problem. We can take that in the next level when we just group all the x together and the function is separable. So this is just a function of x. So we can just write this is from 1 to 9 x dx. So we're going to put all the x together. This is one integral. And we're going to put all the y together. So that is of course only when the function is separable and the limits are constant. Alright. And the rest is simple. We just integrate. This gives us x squared over 2 from 1 to 9. And then y cubed over 3 from -5 to 7. Right. Put 9 in there, we have 81. 81 over 2. And then put 1 in, will be 1 over 2. Times. Put 7 in there, 7 cubed is 343. Oh, yeah, 343 over 3 minus -5 cubed is -125 over 3 So we just do that. Just use a calculator here. Let's put that right. So 81 over 2 minus 1/2. That is 40, by the way. 343 divided by 3 minus a negative, so that's going to be plus 125 over 3, and we have 6240. So where the limits are constant and the separable function, when we have constant limits and separable function, for Forbidden theorem, we can evaluate the integral rather quickly, and we're going to use a lot of this whenever possible. Right. The next one, this is the integral from 0 to 1 for x, 0 to 1 for y, so it doesn't matter because the limits are constant. We can interchange dx dy, so it's not really matter. Just put dy first. Right. Y go from 0 to 1, x go from 0 to 1. Because the limit are constant, interchange the limit, doesn't matter. That's the Forbidden theorem, the actual Forbidden theorem, the function. We'll talk about that later. Alright, next is the function separable. If it is, it will help us a lot. We just split the limits, split the integral like this. So we have e to the 2x plus 3y. Actually, this is a separable function as well. So we can write e to the 2x and then e to the 3y. Because when we multiply two functions with the same base, we just add the exponents. So that's a multiply. So we have a function of x times a function of y. That means separable. Right. Just like the last one, we're going to group on the x together, on the y together. The inside is the y. So this limit is for y, and this is a function for y. So the Forbidden theorem still apply here. We go from 0 to 1, e to the 3y, and dy. And next we have dx from 0 to 1. That is the integral, and the function of x is e to the 2x. So we're going to have 0 to 1 e to the 2x dx. Right. I'll let you do the rest. Just integrate this, and then find the product. That should be simple. I'll just leave you at that. The next one, the limit is not a constant, so this one definitely not Forbidden theorem. We cannot use Forbidden theorem here simply because the limit here has the x, not constant. Right. So we just have to do it like the regular integral. So first we have dy inside. So those limits, those are for y. Right. So with respect to y, x is a constant, x squared is a constant. So we're going to have x squared times y from 0 to 4x, square root of 4x. And then we still have the integral outside. respect to x. Right. Again, those limits are for y. So we're going to put in this for y, put this for y. 0 to 4. X squared. We're going to put this in for y. Square root of 4 x minus where we put 0 in for y. That one cancel. So just have from 0 to 4. Square root of 4 is 2. So we can write x squared times 2 square root of x dx. Square root of x is x to the 1/2. X to 1/2 times x squared is x to the 5/2. We add the exponents. X to the 5/2. 2 plus 1/2 is 5/2. Now integrate x to the 5/2. Integral of that, increase the power by 1, so x to the 7 over 2 over 7 over 2. Evaluate from 0 to 4. Divide by 7/2 is multiply reciprocal 2 over 7. X to the 7/2 from 0 to 4. Right, we're going to put 4 in here and then put 0 in here. But first, that 4 over 7. X to the 7/2. Right, now we're going to put in the 4 and then the 0 and subtract them. This goes to 0 and this 4 to the 7/2, that will be 2 to the 7. Which is 128. So we have 4 over 7 times 128. That is 512 over 7. Right, so this one is not for Binet theorem because we don't have the limit, the constant limits. If it is the constant limits and the function separable, we should group all the x together, all the y together, and evaluate it, then find the product. If not, we just have to integrate without it. Right. So that is the integral. Evaluate double integral in rectangular form. Right. Now we're going to set up the double integral. Right. We're going to sketch. Let we use the calculator here to help us sketch the graph. Just put that here. All right. First, we're going to graph y equal to x squared and negative 6x plus 16 Look like we have to zoom out a little. Right. Should look like we have an intersection here. I mean here and there. And the line is above the curve. Right. So I'm going to sketch real quick. Look like we're going to have a parabola. That x squared and then the line negative 6x plus 16. So it's like that. First we just need to find the intersection of these two. So we're going to let them equal each other. Y equal to x squared and also equal to negative 6x plus 16. Move them on one side, x squared plus 6x minus 16 equal to 0. And we solve for x easily. That will be x plus 8 and x minus 2. So we have x equal to negative 8 and x equal to 2. So those are the intersection. We have 2 here and then negative 8. Right. And in that case, we set up the double integral easily. We have the line above the curve. So we're going to set up the integral like this. There will be 2 integral. First, the limit inside, we're going to have the line is above the curve. So on the top, we're going to have y equal to the function above, negative 6x plus 16. And the bottom is y equal to x squared. So the function above minus the over the function below. In that case, we're going to have dy. So that is, if we look in the y direction, we see the parabola first, then we see the curve. And after that, we're going to ignore, on the x-axis, we only have negative 8 to 2. And that for dx. And that's pretty much it. We don't have any function here, because in this one we only want the area. So that. Next we have e to the x plus y equal to 3 and x equal to 3. Alright. So let's just try to sketch. Because e to the x is going to be positive only, so we don't have to worry about negative x-axis. So this is e to the x. X equal to 3. And x plus y equal to 3. When x equal to 0, y is equal to 3. When y equal to 0, x equal to 3. So we're going to have so bounded by these 3 functions. Looks like we're talking about this here. Right. Now we can either set up dx over dy or dy over dx. Now don't write this down yet. If we look from along the dx, if we use dx in the inside, if we look in this direction, the first thing we see is on the left there are 2 functions. On the right there's only 1 function here. So that's not good. We want 1 function on each boundary. So this direction doesn't work. And we have to put the eye along the y-axis. What we see first is we have the double integral, by the way. If we look along the y-axis, the first thing we see is this line. Say this line. And after that, we see this curve. And that's what we want. 1 boundary above, 1 boundary, 1 above, 1 below, or 1 left, 1 right. If we look in the y direction, we have that. So that's good. 1 boundary on this side, 1 function on this side. So we're going to put dy inside because that will look along the y-axis. The first thing we'll see is this line. By the way, x plus y equal to 3. So y is equal to 3 minus x. So we're going to go from 3 minus x to e to the x. So that is the limit for y. Once we've done that, we just see what will be the limit for x. And this region on the x-axis, we see that is from 0 to 3. So just say 0 to 3 for x. Again, we don't need the function here because we evaluate the area. And we also don't need to write y equal to. We just need to write the limit. So like this would work. We don't need the function here, or just one, if we want the area. Right. So that is to set up a double integral in the rectangular corner. We will just focus on how to set up the integral, because evaluate the double integral is not that complicated. Right. Now on this one, we will reverse the order of integrals. Right, so let's just graph. First we have y in the middle. Right, so we have two functions for y equal to 0 and y equal to ln of x. So y equal to 0. I need to go up. Y equal to 0 is the x-axis. So we go from that line. And ln of x. Let's say let's go like this. So we have dy inside. We look along the y-axis. The first thing we see is this line, y equal to 0. And after that, we see ln of x. And, sorry, we haven't have 1 to 7. X is from 1 to 7. So the region is between 1 and 7. So we talk about this one. Right. So, again, with the y in the middle, y equal to 0 to ln of x, and x must be from 1 to 7. So we only look from 1 to 7 in the graph. Now if we want to reverse, obviously we cannot just reverse the function of reverse the limit by put ln x on the outside. It's not going to work like that. One thing for sure, the x dy dx become the x dy. So that is the order reverse. We determine later. Now, if we're going to put the dy inside, I've used red here. If we just put the dx inside here, we're going to have two functions of x. Remember, two functions of x. And then on the y, we just have two constants, two numbers, two functions, two numbers. Right. Now, if we have dx, which means we're going to look in the x direction, the x-axis. The first thing we see, of course, is this curve. And then we see this curve. So this line is easy. That is x equal to 7. So we go from here to here. If we look along the x-axis, because the x is inside, we go from inside and out along the x-axis, and then worry about the y later. Right. So y equal to ln of x. We raise both sides. E to the y is equal to e to ln of x. Ln and x cancel out. So that is the same as x equal to e to the y. We're going to have the function x equal to something of y. So this is x equal to e to the y, and this is x to the 7. that is the limit for x. Now the limit for the y outside will be easy. We know it's going to be between those two, from 0 to whatever this value says. It's not going to be 3. But because the function y equal to ln of x, so whatever this is, it is going to be ln of 3. The graph is not correct, but we know it's going from 0 to ln of 3. Right. So that is where we'll reverse the limit. Right. On this one, I just wrote a sketch real quick. Inside function is x. We have x inside. So this will have x equal to y squared and x equal to 4. X equal to y squared is the parabola open sideways. X equal to y squared. And then x equal to 4. And then y from 0 to 2. Right. So my question is, are we talking about this one or are we talking about this one? Right. Let's just look at the integral. dx in the inside, right? So we look along the x-axis. The first thing we'll see is the curve and then the line. So it goes from the curve to the line. So we're talking about this region. That one. Right. Now the order reverse, which means the integral from the x dy, the function here stays the same though, phi y, but we're going to have dy and then dx. So we'll reverse the x dy become dy dx. Right. Since we put dy in the middle, this has to be a function of y and a function of y. We go inside out and dy first, so between two functions, between two numbers. Now if we look along the y-axis, what do we see first? We're going to see this line. So what is the equation of this line? And then we're going to have this curve. So if x equal to y squared and both of them positive here, we can say x equal to square root of y. So we go from this line to square root of y, and the x-axis y equal to 0. So we're going to go from 0, because that's what we see first, and then we're going to see the curve. Right. The limit outside on the x, of course, the region, the x values only go from 0 to 4, so that would be 0 to 4. That should be easy. Right. Now we have the double integral in polar coordinates. We either convert or evaluate. Right. First we have to sketch the limits first. We have y equal to square root of 25x squared. So let's take a look at that. Y equal to square root of 25x squared, 25 minus x squared, square both sides, y squared equal to 25 minus x squared, which is x squared plus y squared equal to 5. 25. So we have equation of a circle, radius equal to 5, and the center at the origin. Right. So on that limits, we only go from 0. By the way, x squared plus y squared equal to 25 is the whole circle. But the upper half is where we have y equal to square root of 25 minus x squared. And the bottom half is y equal to negative square root of 25 minus x squared. Since this one, we only go from 0 to 25, so we're only talking about the upper half. And also for the upper half, we go from negative 5 to 5. So we're talking about the whole region here. Alright. Now, we're going to convert this to polar. In polar, what we have is x equal to r cosine theta, y equal to r sine theta, and then dA is not dx dy, but it's going to be r, don't forget there's an r, dr d theta. Right. So this will convert to the function. We don't have anything here, so that's good. The dy dx becomes, that is dA become r dr d theta. So we're going to have the limit worry about later, and then just r dr d theta, and then the limits. Right, the limit first, the r, we look from the center out. We don't go from the 0 to 5 because 5 is the radius, so r go from 0 to 5. And then on the outside, the limit for theta, this region will go from 0 to pi, because that, what we have is from 0 degree to 180 degrees, or from 0 to pi. Right, so 0 to pi, 0 to 5, r dr d theta. This we can use for Binet theorem, because constant limits the function separable. So we're going to group on the dr, and then r, and then the d theta. So for that we will have blue 0 to 5 r dr, 0 to pi d theta. Yeah, the rest is simple. I'll just let you do it. Then of course integrate those integrals and then just multiply them. So that should be easy. So that's where we convert from rectangular to polar. Here we don't have any xy in the function, so we don't do anything. We just need to change the y dx to r dr d theta, and we need to set up the limit based on the graph. Right. Next up, number 10. I'll let you do that integral. Right. 10 we have y equal to this and this. So if we square both sides similarly, square both sides either plus or minus. Squared we have y squared equal to 16 minus x squared. So x squared plus y squared is equal to 16. So we have a circle. radius 4. Right. At the upper half, is positive. The lower half is negative. And so we bound by two functions. And on the x-axis, we have from -4 to 4. So this one we're talking about the whole disk. If we go from 0 to 4 only, we only talk about the half, the right half. Since this one from -4 to 4, we're talking about the whole disk, the whole interior of the circle. Right. So we go to polar. In polar, x equal to r cosine, y equal to r sine, and then dA is r dr d theta. Right. The limit, of course, is the whole disk. Right. So first, we have the double integral. Worry about that later. And then the function though. We have 1 x squared is going to be r cosine square. And r sine square. So we have to replace the function in terms of r and theta. And then dy dx, that r dr d theta. And then the limit are the radius from 0 to 4, and the theta 1 complete revolution, meaning 0 to 2 pi. Here we have r cosine square, so that will be r square cosine square, r square sine square. So this is equal to r square cosine square plus r, factor out the r square. Cosine square and sine square is 1, so this is just r square. So this integral becomes 0 to 2 pi, 0 to 4, 1 over 1 plus r square, and then square, and then r dr d theta. Also by Forbinian theorem, we're gonna, because constant limit on the function here just have r in it, which is good. So we put the r together, put the r on top, so that is the function of r. And then for theta, we just have 0 to 2 pi d theta. This one is easy. That should be just theta 0 to 2 pi, and then we'll do that using substitution. Right. I try to squeeze in the answer here. Oh, sorry. That is from 0 to 4. Right. This is integral using substitution, but I just use a calculator because we can't run out of space here. Alright. Math number 9, 0 to 4. Here's the fraction. I mean that. And then at bottom, so we use x instead of r. Change fraction. That's 8 over 17. That's nice. So this is just 8 over 17. And then this, we just have theta 0 to 2 pi. Put in 2 pi, put in 0, so that's just 2 pi. So we have 8 over 17, 2 pi, or 16 pi over 17. Right. Of course, we can use substitution, but I run out of space. Right. So, first we have to draw the limits to know how do we convert the limit. And that have nothing to do with the function inside. The function inside though, x is r cosine, y is r sine, and then we convert that to r and theta, so that's the function. Dy dx or dx dy doesn't matter, it will be r dr d theta, that in the polar coordinates. Right. Next, find the area of the region specified by the polar coordinate. So we have look like a rose, the graph of a rose petals. Right, see the graph. So on this one we need to graph in polar. Let me update the list first. Right. Now we found the area. Let's just graph this. Again, I'm using the calculator. I'm using the calculator here. So this in polar. So make sure the mode is correct. It should be in polar. And in gradient mode. Right. So that's correct. Y equal 2. So let's graph 6 cosine of 3 theta. Right. See the graph. Too small. Let's zoom in. That's number 6. That's the standard graph. Right. So we have that. Again, let's just sketch that real quick. So it's kind of like that. Right. So because of symmetry, if we can find the area of one petal multiplied by 3, we're going to have the area of the whole thing. Now let's focus on only one petal. We need to determine the limits of those angles, so we can find the integral. Right. To do that, notice in order to draw one petal, we go from 0 out and then back. So that's where r equal to 0. That's where we find it. So we let r equal to 6 cosine 3 theta equal to 0, and then we solve for it. So cosine of 3 theta equal to 0, cosine equal to 0, cosine x values equal to 0. So we're talking about this pi over 2 or 3 pi over 2. So we say pi over 2 plus or minus n pi. Because from pi over 2 we go half revolution and then half revolution, we got those 2 points. Right, divide by 3, we have theta equal to pi over 6 plus n pi. Now, if I choose n equal to 0, sorry, n pi over 3, I have to divide that too. So if we choose n equal to 0, we have pi over 6. And if we choose, we need something negative here. So let's choose n equal to negative 1. We have pi over 6 minus pi over 3, which is negative pi over 6. So look like we have negative pi over 6 and pi over 6. Again, we choose one positive and one negative. The smallest positive and the greatest negative. So pretty much we're trying to get those two. So look like go from pi over 6 and negative pi over 6. It's always worth to go back to the calculator, hit Windows, and then we change to negative pi over 6. And then pi over 6 to make sure that we have the right limits graph, and we see the first pattern, which is good. So it goes from theta from negative pi over 6 to pi over 6. Right. Now we set up the integral to find the double integral to find the limit. We're done with the calculator, by the way. So to find the area, it is going to be the double integral, but this time we use the polar. So instead of dA, we use r dr d theta. The limit now, r in the middle. So if we look along the r direction, meaning from the center out, we only see the graph of the pattern, that the graph of the closed pattern. So that's all we see from the center. So we go from 0 to 6 cosine of 3 theta. That is the limit for r. And for theta, obviously those two. Now, Fubini doesn't work here because Fubini theorem does not work because we have the limit, not a constant. So we have to do it by hand. It's not that bad. Negative pi over 6, pi over 6. R integral with respect to r is r squared over 2. We go from 0, 6 cosine 3 theta, and then d theta. Right, put this in r and put 0 in, we don't have anything. So we just have 1/2 6 square cosine square of 3 theta d theta. 6 square is 36 divided by 2 is 18. Cosine square, that half angle, power reduction. For this one we write as 1 plus power reducing formula from 2 to 1, but the angle have to double, so that will be 6 theta over 2 d theta. Right, 18 times 2, that will be just 9. The 9 we can write either inside or outside, so I'm going to write 9, and then integral sorry, kind of out of space here. Let's write the 9 outside, and 1 plus cosine of 6 theta d theta. Right. Now we have the 9. Integral of 1 is just theta. Integral of cosine of 6 theta is going to be sine of 6 theta over 6 from negative pi over 6 to pi over 6. Right. Sorry, kind of run out of space there. Next, we're going to put pi over 6 and pi over 6. So we're going 9 pi over 6 plus 1 over 6 sine of 6 times pi over 6 cancel out, so that's sine pi minus 9 negative pi over 6 plus 1/6 sine of negative pi. Really run out of space. Sine of pi is 0, sine of negative pi is 0. Combine this together, we have 9, so 3/2 and 3/2. So that gives us 3 pi. So that one is equal to 3 pi. Right. So the area of this one petal is 3 pi. We have 3 of them. 3 pi times 3, 9 pi. So the total area is equal to 3 times 3 pi is 9 pi. Right. So this is 3 over 2 plus 3 over 2. 3/2 and a 3/2 is a 3. 3 pi for one petal times 3, we have 9 pi. So that's 11. Right. And triple integral. Evaluate this is very simple. I'll just look at the setup first. We're going to write the triple integral to evaluate this. So let's put the limit. The integral. If I have my default choice is usually just reverse alphabetical. So dz, dy, dx. The function is nothing inside. So first we look for between the two functions of z. So from here, if we solve for z, z over 3 equal to 1 minus x over 4 minus y over 6 and times 3. So z equal 3, 1 minus x over 4 minus y over 6. That is the limit for z. And this is cut from the first octant. So the first octant. So if we have to sketch x, y, and z, we're going to have a plan, something like that. So if we look along the z-axis, this might be difficult because in 3D. So we look from the bottom, looking up, we see the x, the z equal to 0 first. And then we see that function, the diagonal plane on the top. That's for dz. Now for y. For x and y now we just let z equal to 0. So we're going to have x plus x over 4 plus y over 6 equal to 1. Again, we solve for y. We have 6 times 1 minus x over 4. So now that we're done with the z, we only look on the x and y coordinate. And we have a point on the x-axis, a point on the y-axis. So we're looking for this. First we see is y equal to 0, and then whatever this is, this line. So we go for y equal to 0, and to this y equal to 6, 1 minus x over 4. And finally, on the x-axis, we let y and z equal to 0. So x is x over 4. If we let x equal y and z equal to 0, then we only have on the x-axis x over 4 equal to 1, so x equal to 4. So we go from 0 to 4 for x. Right. So first, it is between two planes. Our function of z, so z equal to that. When we're done that, we let z equal to 0. We only have y and x. Limit for x, y. And then when we're done that, y and z equal to 0, we only have x left. And then we find the x values. So that's what we have. Right. Next, we have that. So triple integral. Limits are not constant, so for Forbidden theorem out of the window, cannot use that because non-constant. So we just do inside now. Inside is an x, and there's no x here in the function. So we're going to have yz times x, where x goes from 5 to z. Sometimes it's not clear, we can always write the limit like this. The limit with particular variable. And so that is what we did, was just do the inside integral. That's what we have here. So the inside integral gives us this. Right. Outside still the same. We put z in here, we have yz squared. And to put 5 in there, we have 5yz. Dz and dy. Now let's do this integral. So just inside out, 0 and 2 still the same. Yz with respect to z will be y z cubed over 3 minus 5y z squared over 2 from z equal to 2 to z equal to y squared. So that integral is this dy. Right. First I'm going to put in y squared here. So now we have y squared cubed is y to the 6, and then put y squared here. Y squared square is y to the 4th. Subtract. Now put 2 in here. Y 2 cubed is 8 over 3 minus 5y. 2 square is 2, is 4 over 2, which is 2, so we have that. And then dy. Right. We simplify inside. Look like that will be y to the 7 over 3 minus 5 over 2 y to the 4th times y to the 5th. And combine this, we have a over 3. That's 20, so that just be extra careful here. So that is negative a over 3y minus 10y. A over 3 minus 10 is minus 22 over 3 with an extra minus, so that plus. (22 over 3 y). And I will just integrate. Right. Just use the calculator here and see if we have it. (0 to 2). That's fine. Minus 5/2. Plus 22. And we have negative 4 over 3. Of course, we can just do this by hand, but that's just a single integral. That should be easy. Right? Yeah. Right. Next, we have this one. Again, inside and out. Inside, we just have dz, so we have that. We're going to do that first. So let me update the list. So evaluate. Kind of hard to just say this is 13 and setup that's 12, and what we're doing here is 14. Find yeah, that kind of like 12 too. So just delete this. Yeah. Right, we're good. Right. Actually, we have evaluate number 14. That's what we're doing here. Right, sorry about that. Right, inside and out. We're going to do this first. With respect to z, will be z squared over 2. And then we have r d theta still the same. Put 3r in here, we have 9r squared over 2. That's it. 0 give us nothing. And then times r dr d theta. And that gives us 9r cubed over 3 dr d theta. Right, originally it has the variable limit, so we cannot use Fubini theorem. Right, at this step, now we can use Fubini theorem because all of this function of r and then d theta. So we just have for theta 7 to 10. And then what's next is dr. I don't know how we go from 2 to 3. Really, sorry. And that's a cube. Right. So I'll let you finish the problem. That should be easy. Two integrals multiply together, and that's what we have. So we're trying to use Fubini theorem as much as possible because that simplifies things a lot. Only use Fubini theorem when we have the constant limits and the separable function. Now we go to cylindrical and spherical coordinate. Right. First, the center and upper part, we have this one, one of them. This one is spherical and a sphere. So first, we set up using spherical coordinates. So spherical coordinate, we will have three things. Rho, phi, and theta. Rho is the radius from the center out. That part's easy. The phi is the angle from the top, from the north, on out. And then the theta is the standard from the positive x-axis. Right. So this one, set up the triple integral for the volume of the sphere, rho equal to 3. So pretty much trying to draw a sphere here. Usually we just draw a sphere first and worry about the coordinate axis later. Yeah, of course you see that look a little better. Right. So in spherical coordinate, it's going to be triple integral. The dv is going to be rho square sine phi sine of phi of phi. The rho, limit for rho, limit for phi, limit for theta. Right. The rho is limit by the sphere, so this is easy. The rho will go from 0 to 3. Right. Next, for phi, we go from the North Pole. Now, it's just like you see the Earth or the globe from the North Pole to the South Pole. That's actually the angle phi. So that of course is 180 degrees On the top, the north pole is 0 and the south pole is 180 or pi. So we're going to go for phi. We go from 0 from the top to the bottom, the south pole of pi. And we go one complete revolution all the way around. So will be 0 to 2 pi. So outside limit 0 to 2 pi, one complete revolution. Limit for phi, the north pole 0 to the south pole pi, and then theta from 0, and then rho from 0 to 3. Right, and we always have to have rho square sine of phi in there. Right, so that just set it up for the sphere. Next we have the region bounded by the cone, and then above by the sphere. So look like this is an ice cream cone. So we have I just draw the cross section over here. So first we have a cone given by phi equal to pi over 4. Of course the angle phi is going from the north pole down there, so phi is pi over 4 is here, and here is phi equal to 0. So that the angle that's web from 0 to pi over 4. Right. So we have one of them. So again, the integral, triple integral, still the same way. Rho square sine of phi d rho d phi d theta. Right. Now, first the limit for the radius rho. Rho we go from 0, and we just look from the center straight out, and we only see the sphere. So rho equal to 0 to rho equal to 5, because that's the sphere equal to 5. Next, the angle phi. Go from 0 to the north pole out to the edge of the cone, pi over 4. The north pole. And then d theta. We go one complete revolution all the way around, so 0 to 2 pi. Right. So that's good to know, but that's what they asked for. Sorry. What I asked for is in cylindrical coordinate. Right, so this is in spherical. Right, keep that in back pocket. Now we're not going to do this, even though it's correct. Now we're talking about cylindrical coordinate. So which means it's going to be z didn't read the question. Tangent pi over 4 is 1. So this is z equal to r. So the surface of the cone given by z equal to r. Also in this triangle, right triangle, we have z square plus r square equal to rho square. So from there we can have we're going to solve for z because we need z. So z equals square root of rho square minus r square. So since we have rho equal to 5, again z is equal to square root of rho square minus r square. So we can say 25 5 square minus r square. So that is the limit for z. So we say z go from z equal to r, z equal to r, to z equal to square root of 25 minus r square. This is a lot better if we use spherical coordinate, by the way. So we're done with that. We're done with the z. Now we go to r and theta. That's easy though. Now we just look on the circle, on the disc particular. Now we look at this cross section. That is a disc we're talking about here. Right. So now, since rho is equal to 5, we have to find r. With this right triangle, r and rho opposite over hypotenuse. So sine of that angle is equal to opposite over hypotenuse. So r is equal to 5 and sine pi over 4. So we can show that r is equal to 5 square root of 2 over 2. That is the outside radius. And then the limit will of course go from 0 to the edge of the disk. And then theta would be easy. Limit for theta, limit for r is from 0 to 5 square of 2 over 2, and then d theta just 0 to 2 pi. Right, so that's 16. We set it up. Right. Now we use the cylindrical to find the volume. Now we're just going to set it up. So if we have z equal to, that is a paraboloid open up. This is paraboloid open down. So we have one open up and one open down, like that. So the one above, that one below though, and the one above. So if we set up the limit, this one in cylindrical coordinate, dz or dr d theta. This one we need to do the integral. I'll let you do the integral. We just set it up here. To limit for z, obviously that will be easy. We have between those two, but notice that we have x square and y square here. X square plus y square is r square. So this will be just r square minus 7. And likewise, this would be 43 minus r square. That will be the limit for z. Z equal to r square minus 7 up to 43 minus r squared. That is for z. For r, now when we put those two together, now we just consider the cross section. We're talking about this. That is, of course, the intersection of those two. So we let z equal to 43 minus r squared equal to r squared minus 7. So that gives us r squared, 2r squared equal to 50. So r squared is equal to 25. So that circle here is the intersection r squared equal to 25. If we plot that on two-dimensional, we just have 0 to 5 because r squared is 25, so r is equal to 5. That on the edge though. If we write the limit for r, it's going to be from the center to the outside. So be r go from 0 to 5. And then the theta again will complete one revolution. Right, I'll let you evaluate that integral. Right. Right. Next, we have just the cylinder. Bounded above by z equal to 3, and then xy plane, which is z equal to 0. So that should be easy on the z. Cylindrical would be dz or dr d theta. And the limit for z from 0 to 3. That part easy to set up. Now, only need to go from r and theta. Now let's graph 6 cosine theta and see what happened. I believe the calculator is still in polar coordinate. So let's graph it. 6 cosine theta. Alright, we need to change from 0 to 2 pi. Right, look like a circle. I had to sketch that real quick. Right. But look like, if we look from the R, from the center out, we only see the curve. So the R will go from 0 to 6 cosine theta. And then the theta, that's interesting, because look like this, we go from negative pi to pi. So it's negative pi over 2 to pi over 2. So let's change the windows and change the limit to see if it works, because it does to go like from this line to that line. So negative pi over 2 to pi over 2. Yes, so we don't need to go from 0 to 2 pi. It only go from this angle to that angle. If we want to make sure it, we go extremely slow here. Let's say pi divided by 200. So we plot a little bit slower. It stopped there. Right, so just one complete revolution. We don't want to go over many times. Anyway, so to go from 0, negative pi over 2, and then pi over 2. Right. So that, again, I will let you evaluate it. Alright, next one. This we use the spherical coordinate. Yeah, we cannot really update any thing on the list yet. Spherical coordinate. Right. So x squared plus y squared plus z squared. So this one is 3 because that one is rho square. Yeah, so we get that without any effort. Xy plus y squared, that is r square. So this gives us z equal to r. Right? Sorry. Yeah, z equal to r. And then rho equal to 8. Right. Those two graphs. So again, we have above by the sphere, and then on the side by the cone. So actually this one is exactly like the one here, number 16, just given differently. So if we look on the cross section of the R Z axis, again the theta angle is here, just use red. So the phi angle is there. That is R, that is Z, and this is rho. So with respect to this right triangle, with this angle phi, opposite over adjacent is tangent. So tangent of phi is equal to opposite over adjacent. Since they're equal, this is equal to 1. Inverse both sides, we have the phi is equal to pi over 4. So that, of course, if you look on number 16, that is actually the cone given by this edge. Pi over 4. And then the rho, of course, we go from 0 to 8. That part easy. And then the theta 0 to 2 pi, one complete revolution on the way around. Right. So triple integral in spherical coordinates, rho square sine of phi d rho d phi d theta phi of phi. It doesn't matter. Alright, rho square, I mean rho, that's one easy. Go from 0 to 8 from the inside to the edge. Rho equal to 0 to rho equal to 8. So that is the rho. The phi or the phi from the North Pole to this angle. So phi 0, phi pi over 4. And then d theta, so that by can stand at 0 to 2 pi. So again, I will let you evaluate this integral. By the way, on the test, if I ask this question, I will only ask you to set up the integral. So let's change number 19 and 20. Actually, 17 to 19, 17 to 20. Just evaluate the integral. I will put that here. 17 to 20. Just set up integral. So we don't need to evaluate because the point is just how to set this up. Just capitalize. Right. just set up the integral. Well, don't need to evaluate it because that's the point of set it up. Evaluate triple integral. That's not that bad. Right. Number 20. X squared plus y squared plus z squared. Once again, this is rho square. So this without any effort, we have rho equal to 6. That's the limit. One of the limit. Right. The next one is a little more complicated. X squared plus y squared. That is r. Unfortunately, r is not in the spherical coordinate. Only rho, theta, and phi. There's no r in it. So how do we get r here? Again, in the r and z coordinate. R and z and rho. Again, z is not in the spherical coordinate either. We only have r and we only have rho and phi or phi. So we have to write this opposite. R is opposite, rho is hypotenuse. So that's going to be sine of phi is opposite hypotenuse. So we can say r is equal to rho sine of phi or sine of phi, and then divide by the sine on both sides. Rho equal to 2. 1 over sine is cosecant. Right. So if we talk about this, the region lies inside the sphere, so we're going to have a sphere. Actually, we'll have the cylinder first. And then we have a sphere. So one on the top and one at the bottom. Yeah. So the sphere bounded by the above and the bottom, top and bottom. So in terms of r, in terms of the limit though, so let's put the limit. Again, this integral is much easier to do in cylindrical coordinate because simply we have a cylinder. Right. But if one is spherical though, rho square sine d rho d phi d theta. And this one, if we actually use this integral, that will be extremely difficult thing to do because we will see. First, if we take a cross-sectional of R and Z, we have a sphere on the top, and so we'll have to look at this one. And there's a problem. Within this portion, we have from 0 to the edge of the sphere. And when we have this part, we have this angle from 0 to the edge of the cylinder. So the limits are not the same. So this one we have to split in two. Integral. So that's good that we don't have to evaluate it. Right. So the reason we split in two because for this angle above, the outside function is the sphere, inside 0. For this one, the outside is the cylinder. So the limits are not the same, so we have to split. Right, so where do we split? Where's the angle though? So we actually have to find it. We'll let those two equal each other. This is x squared plus y is 4, so this is going to be 4. So we have z squared plus 4 equal to 36. So z squared is equal to 32. So z is equal to square root of 32. Right. If z is equal to square root of 32 and rho is equal to 6, we can find the angle phi there, or find adjacent hypotenuse cosine of phi is equal to adjacent hypotenuse square of 32 over 36. So this one is much better to use cylindrical coordinate because we have the cylinder. Use spherical is very difficult. And then we take the cosine inverse of this. That gives us the angle. That's where we break here. So that is cosine inverse of rho is equal to 6. Sorry, not 36, to 6. Right. Now, the easiest part of theta 0 to 2 pi, we don't have to worry much about that. Now, first, if we go from 0 to that, whatever this angle is, let's call that angle as alpha, so we don't have to write the whole thing. So go from 0 to alpha. If we go from 0 to alpha, we only talk about that part. So go from 0 to the sphere. The sphere is, equation is rho equal to 6. So we go from 0 to 6 there. Right. For this one, if we go from alpha to pi over 2, we will talk about from 0 to the edge of the cylinder given by this equation. So 0 to 2 cosecant of phi. Right. So that gives us half of the problem. Okay. So where's the other half? Notice that the one we have is the whole thing, like the upper half and the lower half. If we cut only from 0 to 90 degrees, that's only the upper half. So we just need to multiply by 2. So obviously, if this one we use the cylindrical coordinate, we have to be this complicated. But if we want the area, the best way to set it up with the cylinder is using cylindrical coordinate. That will be a lot easier to do. We don't even have to split the limits like this. Right. Because the limit in spherical for rho is going from, in this case, from 0 to the edge. Either we see the sphere on the top or the cylinder on the side. So because the limits are not the same, we have to split the limits. Right. So that was that. Next. The center of mass. Right. So the center of mass. First, let's sketch the regions. What do we have here? 25 minus x squared, so that looks like upside down parabola. And here from -5 to 5. So if we want to set up the integral, it will be from -5 to 5 for x and y from 0 to that. But this we have the density function. So in this case, we're going to find three things: the mass, and then the moments in the x direction and the y direction. Right. So first the mass. It's just the limit for x and y, but with the density. Let's do dy with and then dx. For y, limit for y, we go from y equal to 0 to that curve. So we go from y equal to 0 to 25 minus x squared. And then the limit for x from -5 to 5. So that gives us the mass. Let's just do this quickly. Now we do the inside first. Integral with respect to y. So we have 5x squared is a constant with respect to y. So we just have y from 0 to 25 minus x squared. Just dx. It's out of ink dx. Right. And then we put 25 minus x squared into y, and that's all we have. So we just have 5x squared 25 minus x squared dx. Right. I'm just going to use the calculator here. First, I just change back to function, so we don't have to show up theta. Right. -5 to 5. 5x squared times 25 minus x squared right. We have fraction here. Right. Look like there's a little bit off there, so we look like we have this. Is that? Really? Maybe we need more 6. Right. What was that, by the way? Don't worry, but I try to say sometimes, that's all. But right. So look like 4166 plus 2/3. That have to come up. Right, so that over 3. Right, 1, 2, 4. There. Right, so that is the mass. Next, the moment in the x direction and in the y direction. So that will be capital M x and capital M y. So the integral almost, put the calculator away for a moment. For the moments. The integral is the same. Right, the difference here is now we have the moment in the x. We're not going to stick an x here because that's not what it is. The moment on the x meaning that the distance to the x-axis. Of course, the distance to the x-axis actually is the y, so we're going to stick the y in here. Likewise, for the moment my, the distance to the y-axis is of course the x value, so we're going to stick an x here for my. Right, so let's do this. So that's negative 5 to 5, 0 to 25 minus x squared. What we have y squared over 2 dx. So we x squared, the limit 25 minus x squared. Right, 5 over 2 x squared. If we put 25 minus x squared in here, we have 25 minus x squared dx. Right, let's use the calculator again. Hope it will be more useful this time. Right, let's go back up. We have here. Right, so instead of that, we're going to divide by 2. Five over 2 instead, and instead of 5. So 5 have x squared, and then 25 x squared, and then let's put another square here. Right. Do we have fraction here? No. Let's just minus 29,761. If we just have that, do we have the fraction for that? Nope. Okay, let's do this by hand. Right, actually, let's just add that number. Right, I'll just keep that for a moment. Right. So, I just go to dy. We'll get back to this. We should get a much smaller number, so we don't have to worry about this. Right, so that is 5x cubed. Oh, which is much better. Right, so first we have the y here, so negative 5 to 5. Integrate with respect to y. There's a constant, so that's just y. Go from 0 to 25 minus x squared dx. So 5x cubed, 25 minus x squared. Right. Much better this time, because this is an odd function with symmetric limits. So that is equal to 0. So at least that one is easy to calculate. This one, just keep that. I'll just keep that number on the calculator for now. Right. So, and finally we have. I just want to write the decimal here because we run out of space if we actually do this integral. Right. This equal to 0. And finally, we're looking for the center of mass. The x bar is equal to my over m. So my 0 over the mass, doesn't matter what it is, it's still 0. The y bar on the y corner is going to be mx over m. Right. I just use the calculator to get the estimate here because we don't have. So that is mx divided by m 125 hundredths. So we have about 7.142 something. I doubt this can turn into any fraction. Oh, it is. So it's good. So we're good. 50 over 7. Actually, yeah. So the center of mass is 0 and 50 over 7. Right. So the mass is just the integral, the area, but with the density. Density times area is the mass. The mx, going to stick the y because that's the distance to the x-axis. My, we're going to put the x in it because the distance to the y-axis is x. Do that integral. X equal to x bar, the center of mass, the coordinate in the x direction is my over m, and then mx over m for y bar, and we have that. Right. Next, so we're done with the center of mass. That is number 21. Now we go to the last part about transformation. Right, find the Jacobian. The 22 is so the Jacobian, pretty much the partial derivative of xy with partial derivative of uv. So I'm just going to write the partial x or partial u x v, and then y u y v. Right. You just find the partial derivative, put in the determinant, and do that. I'll let you do that problem. Right. I'll do 23. We have x, y, z here, the variables. That's the determinant. So first we have the derivative with respect to x of x with respect to u, v, and w of y with respect to u, v, and w, z, u, z, v, and z, w. Right. So we have x, y, z, the dependent variable over independent variable. Right. This with respect to u is 2, with respect to v is 3, with respect to w is 0. Next one, with respect to u is 2. With respect to v, there's no v there, but they're -3. And for z, with respect to w is with u is 0, 0, and 1. So 3 by 3 determinant. Of course, this is just like the cross product, kind of, or the cross product is kind of like 3 by 3 determinant. Right. So the 2 cover the row and the column will be 0, 0, -3, and 1. And next, -3, we have 2, -3, and 1. And then the last 0, doesn't matter what it is, it's going to be 0 anyway. So this also 0, because 0 plus 0, that's 0. So only have this. And that gives us -3 times 2, so -6. So that's all we have. A 3 by 3 determinant. Right, so that is evaluate the Jacobian. Again, all the partial derivative of dependent variables give us the row, independent variable give us the columns. That is 22 and 23. Interesting. Last one is the chain of variable theorem. Right, this one is nice enough to give us the transformation. We don't even need that. Right, so first we have, I will change these two equations. Move x and y to one side, and I will say x plus y equal to 1, and then x plus y equal to 4. These two, if I move the 2x to the other side, -2x plus y equal to 2, -2x plus y equal to 5. Don't even need to draw it. X plus y equal to 1. So y equal -x plus 1, -x plus 1, -x plus 4, 2x plus 2, and then 2x plus 5. So we talk about this. Right, of course, that region, if we set up the limit, it will be very difficult. But like I said, we don't even need the graph here. Right. But one thing we notice is, if we let u equal to this, will be u from 1 to 4. So let's write, let u equal to x plus y, then we have the limit for u is between 1 and 4. And we're going to let this equal to v. V will be between 2 and 5. Right, so we have the limit for u and v. We have the the transformation. Right. What do we need to do? Right, chain of variable theorem. Let's just write the theorem first. So first we're going to have this. We're going to change this into u and v. So first we have to rewrite this a function of u and v. So what is y equal to? Right, we need to solve for y. Right, x plus y is equal to u minus 2x plus y is equal to v. So first we need to eliminate x so we can solve for y. To do that, we multiply 2 on the top equation. 2x plus 2y equal to 2u. Negative 2x plus y equal to v. If we add side by side, 3y is equal to 2u plus v. So y is equal to 2u plus v over 3. Right. So now we have 5. Y is going to be 2u plus v divided by 3. Right. And then we have to have the Jacobian of xy over uv, and then du and dv. This is easy. U is from 1 to 4, and then v is 2 to 5. So we have everything except for the Jacobian. The function is easy. Y is 2u plus v over 3. Right. Now how do we find the determinant of Jacobian matrix? Notice that this is xy over uv. We don't have that. We only have u equal to something x, v equal to something y. We can still use that, don't worry. So now we're trying to find the Jacobian here. So I find u and v instead, because that one out of ink. Notice this is not the same as the Jacobian we find, but that's alright. So that will be u with respect to x, u with respect to v, u with respect to y, v with respect to x, and v with respect to y. And this is u with respect to x is 1, u with respect to y is 1, v with respect to x negative 2, v with respect to y is 1. Determinant of this is 1 minus 2 so that is 3. So the Jacobian of uv with respect to xy is 3. Now we want this, all we need to do just flip both sides. So we just do the inverse on both sides. So xy uv is equal to 1 over 3. So that we don't have to actually solve for x and y in terms of u and v. If we can have u and v in terms of xy, we just do that and then just do the reciprocal. Finally, the integral is from 2 to 5, 1 to 4, 5, 2u plus v over 3. The Jacobian is 1/3 du dv. Multiply all the numbers, 5 over 9, 2u plus v du dv. Right. I'll check the 5 over 9 outside. Now we integrate with respect to u. Give us u square plus vu from 1 to 4. Yeah, 2u integral up to u is u square, and v is a constant, so we stick a u to it. Right, so we're going to put 4 in for u, 4 square plus 4v minus 1 square, 1 in for u minus v. So I have 5 over 9, 2 to 5. 4 square minus 1, 16, minus 1 is 15. 4v minus negative, so that's plus 5v. Right. I just trying to use the calculator here. Have 97 over 5. Notice we need to multiply by 5 over 9. So we have that times 5 divided by 9. Alright, that's a little bit off. Let's see with the calculator, with the answer on the back. Let's see what's wrong there. I need to go back and check it. Right, I know. Right, first the function phi multiplied by 2 to x to y to u minus 2. That cancel 3y 2u plus v divided by 3. Right, so that's it's good there. U from 1 to 4, it's good. V 2 to 5, that's good. The integral, right? The Jacobian here. Right. I don't know. This is supposed to be a plus, so that should be a 3. Sorry. This should be a plus. That should be a 3. Let's do that again. Calculator. Let's change that to a 3. Right, 76 and 5 times 5 divided by 9, and convert this to fraction. Right, 85 over 2. Oh, so that's good. Yeah, sorry, this will be a plus. Right, let me zoom out and see the whole problem. So change a variable. Again, we don't even need to be given this. From the limits, we can deduce that u is better to be x plus y. One of them is u, one of them is v. It doesn't really matter. But if we choose that, then we only have 2 variables. So the first one's u, second one's v. With that, we have the limit as well. Right. So we have the change of variable from x, y to u and v, and the limit for u and v, which is good. So we have everything except the Jacobian here, asking for the partial derivative with respect to xy over uv. We don't have that. In order to do this, we have to have x equal to something, y equal to something. we only have u equal to something and v equal to something. So we still do that, get a number. That is uv over xy. If we want the reciprocal, we just flip them. So we flip that, give us 1/3. Now the function have to be in terms of uv as well. So that's why we have multiply the Jacobian and then the limit for u and v is there. Right. And the rest just evaluate the double integral. So pretty much that. Right, so pretty much from this part. Right. With that, let me just put this here, number 24. With that, we cover everything on the topics for test 3. Sorry, this is a little bit longer than I anticipated, but at least we cover everything. I hope this helps you to prepare for test 3. As always, thank you for watching.